Our universe has 3 spatial dimensions and 1 temporal dimension, but some theories say there might be more. Written as space-time, it is 3 plus 1 dimensions. For instance, string theory suggests there are 9 spatial dimensions and 1 temporal dimension. But we don't see these extra dimensions. Does this mean that string theory is wrong? Not necessarily. It can be hard to see the extra dimensions. Let's look at a simpler example. Take a flat surface and transform it into a cylinder by rolling it up. A long, narrow cylinder looks like a one-dimensional line. Nonetheless, it remains a 2-dimensional surface, but with its second dimension compressed into a tiny circle. Space beyond 3 dimensions can also be compressed into tiny circles. For instance, a 9-dimensional space on a larger scale can appear as a 3-dimensional space. We need an experiment to find out if our world has more than 3 dimensions. Let's consider a 2-dimensional example and observe how a particle moves. Particles move in one of the non-compactified dimensions, and also in another dimension, a tiny circle that is hidden from our view. Is it feasible to detect this motion experimentally in the extra dimension? Let's examine how a particle moves in a circle. We need to bear in mind that we must use quantum physics to describe our world on a small scale. Thus, our particle is described by a wave function, which we can denote as psi. In quantum mechanics, we have the following equation. The Hamiltonian operator H acts on psi to give E times psi, where E refers to the particle's energy. The distance around the circle is represented by x. We can assume our particle is free, i.e. there are no forces acting on it. The Hamiltonian operator for the free particle is minus h bar square over 2m times second derivative with respect to position. Here, h bar represents the reduced Planck constant. This is just a number, a very small number, and m is the mass of our particle. A general solution to this equation can be expressed as follows. Psi of x equals a constant coefficient multiplied by e to the power of I h bar over 2 e times x, plus a different constant coefficient multiplied by e to the power of minus I times the same quantity as in the first term. Here, I represents an imaginary unit. These solutions describe waves, and the first term corresponds to waves moving towards the positive sign of x. The second term corresponds to waves moving in the opposite direction. We would obtain the same outcomes if the particle only moved in a straight line. But how do we consider that the particle moves in a circular path rather than a straight line? When we travel around a circle, we return to the starting point if we travel the distance equal to the circle's circumference, which is 2 pi r. Therefore, our solution or wave function must be periodic. This means that the value of psi at 0 must be the same as the value of psi at 2 pi r, where r is the radius of our circle. By plugging in our solution to this equation, we obtain the following expression. This equation can only hold if the following relationship is true. H bar over 2 m e multiplied by 2 pi r is equal to an integer multiplied by 2 pi. This is because e to the power of the integer multiple of 2 pi is equal to 1. We can get an equation for the energy of our particle. The energy of the particle on the circle is not arbitrary, it is quantized. It can only be the same as some particular values. Therefore, this energy equals some fixed amount that contains the particle's mass, the reduced Planck constant, and the radius of the circle multiplied by an integer squared. If k equals 0, then the energy equals 0, indicating a non-moving particle. If k equals 1, then the energy equals a following constant. If k equals 2, then the energy equals 4 times the previous value, and so on. This concept can also be understood with the help of a diagram. As the particle is defined by a wave function, the function must match a circle. This is why only specific values are permitted. Let's work out the tiniest amount of energy required to move this particle in a small circle. The smallest amount of energy will be when k equals 1, because k being 0 results in a non-moving particle. Let's crunch some numbers. H bar is a constant of order 10 to the minus 34. The radius of the compact dimension is unknown, but it must be very small. We will use the Planck length, which is of order 10 to the minus 15 meters. Let's assume particle with a mass of electron, which is 10 to the minus 31 kilograms. By plugging in these parameters into the equation, we discover that the minimum energy required is 10 to the power of 33 joules. Thus, We require an accelerator that can boost particles with 10 to the power of 39 times the energy of the LHC. Consequently, it's challenging to determine if there are any extra dimensions. In simpler terms, if we operate in a low-energy environment, any possible extra dimensions do not have an impact on us.